In the last video, we learned this method called U-substitution, and you might have found it really confusing. I think most students do the first time they see it, but that's okay. What we're going to do in this video is just get a lot of examples using the U-substitution method. And I'm actually going to cheat a tiny bit. One of the big challenges with the U-substitution method is picking what U should be equal to. And for the first 2 or 3 of these examples, I'm going to pick that for you. I'm going to tell you what U should be, and then we'll just work out the rest of the algorithm. We'll get a lot of practice, we'll get kind of comfortable with the algorithm, and maybe as we start to get comfortable with the algorithm, it'll be easier to understand why I picked U to be equal to whatever I picked it to be. So in this problem, for example, when we're trying to figure out the antiderivative of 2e to the 2x plus 1 dx, I'm just going to tell you that you should let U be equal to 2x plus 1. This first step where you have to determine what U is already done for you. And I want you to pick it up from here. Where would you go next? Well, remember, our second step is always to take the derivative of that thing that we called U. So I need to know what's the derivative of 2x plus 1. The derivative of 2x plus 1 is the derivative of 2x plus the derivative of 1. And the derivative of 2x is just 2. The derivative of 1 is 0. So the derivative of 2x plus 1 is just 2. My second step is done. My third step is to solve my second step for du. It's to treat this like it's a fraction and multiply both sides of the equation by dx. So I get du is equal to 2 times dx. That brings me over here to my fourth step, where I'm going to substitute this line and this line into this original expression. So how do I do that? Well, what I have is e to the 2x plus 1 power, but instead of writing 2x plus 1 power, I can write u. Left behind, I would still have this 2 and this dx. However, 2 dx is the same as du. So instead of writing the 2 and instead of writing the dx, I can replace that with du. I've substituted the first and the third line into this expression. Doing so got rid of all of the x's, and I now have an integral that I can figure out. What's the antiderivative of e to the u power if I'm treating the u as the variable? Well, that's easy. The antiderivative of e to the x is just e to the x. So by the same logic, the antiderivative of e to the u would just be e to the u. I guess plus c if you want to be technically correct. Great, that's the antiderivative. So that's my final answer. Well, almost. You just don't want to leave u's in your final answer. So let's substitute back. Our fifth step, we change the u back to 2x plus 1, and we get e to the 2x plus 1 as our final answer. Early on, when this is still new to you, I'd recommend taking the derivative of your final answer. What's the derivative of e to the 2x plus 1? Well, I'd have to use the chain rule. The outer function is e raised up to some stuff. The inner function is that stuff. So when I'm taking the derivative, I take the derivative of the e raised up to the stuff. E to the x is just e to the x, so e to the 2x plus 1 is e to the 2x plus 1 times the derivative of 2x plus 1. The derivative of 2x plus 1 is just the number 2. So the derivative of e to the 2x plus 1 is e to the 2x plus 1 times 2. In other words, 2e to the 2x plus 1. Exactly what we started out with here. Oh, cool. Sounds like I got the right answer. Let's do another one of these. What if we were taking the derivative of 2e to the 5 minus 3x? You might already have a guess for what u should be equal to. I'm just going to tell you, we're going to let u be equal to 5 minus 3x in this problem. If u is 5 minus 3x, then du over dx is equal to negative 3. The derivative of this is just negative 3. If I solve this equation for du, I get du equals negative 3 dx. And now I substitute line 1 and line 3 into this integral. I see my e raised up to the 5 minus 3x power, but instead of writing 5 minus 3x, I'm going to write a u, so I get e to the u power. But then you run into a little trouble. You're like, okay, now I'm looking for this negative 3 dx, and I don't see it anywhere, right? I see a 2 dx, but not a negative 3 dx. That's okay. Sometimes the pieces won't fit quite as perfectly as they fit up above. But I have an equation here, right? du is the same as negative 3 dx. So I can divide both sides of the equation by negative 3 and get negative 1/3 du is the same as dx. The reason you might want to do this is because we know there's a dx here. There might not be a negative 3 dx, but there's certainly a dx. So I can just replace that dx with negative 1/3 du. So I still have this 2. Instead of e to the 5 minus 3x, I have e to the u power. And then instead of writing dx, I'm going to write negative 1/3 du. So this is my answer? No, we haven't done any antiderivatives yet, right? All we've done is this substitution. All we've done is rewrote this integral, which we don't know how to take the antiderivative of, as this integral, which we do know how to take the antiderivative of. And you might be looking at this and be like, I'm not sure I can take the antiderivative of that. I bet you can, because the 2 and the negative 1/3 are just constants, right? So we can pull those out in front of the integral symbol, and what we have to take the antiderivative of is e to the u power du. And the antiderivative of e to the u power is just e to the u power plus c. So my antiderivative is just negative 2/3 e to the u plus c. You shouldn't leave your answer this way because u was something that we chose to introduce in this problem. It's 5 minus 3x. The original question only had x's, not u's, so we should substitute back, and for our final answer, we'd get negative 2/3 e to the 5 minus 3x power plus c. All right, part C. I want to switch part C a little bit. What I want part C to be is 1 over 3x minus 1 dx. And I'm again going to tell you what u should be equal to. You can guess if you want, but I'm going to focus less on y and just take as a given that u should be equal to 3x minus 1. We'll go back later and talk about why u should be 3x minus 1. My next step has been to write du over dx equals, what, 3 in this case, the derivative of 3x minus 1. But I'm going to cut out this second step and jump straight to the third step and write that du is equal to 3 dx. Because I think you're advanced enough to kind of see that, right? We don't need to write du over dx equals 3, and then du equals 3 dx. We don't need that extra middle step. I bet we can cut out 2 at this point and go straight from 1 to 3. If you're not comfortable with that, fine. Put step 2 back in the middle. I'm just telling you most people don't end up writing that step. The other thing that I want to do a little bit differently in part C is I don't want to stop here with du equals 3 dx. When I look at my question up here, I don't see a 3 dx floating around, but I do see a dx floating around. So what I want to do is solve this for dx. I want to multiply both sides of this equation by 1/3 to get 1/3 du equals dx. I now have all the pieces that I need over here to evaluate this integral. First, I'm going to rewrite the integral using u as the variable instead of x as the variable. So instead of 1 over 3x minus 1, I would have 1 over u. And then instead of dx, I would have 1/3 du. This is not an integral that we know how to take with our rules, but this is an integral we know how to take with our rules. The 1/3 is just a constant, so I have 1/3 times the antiderivative of 1 over u du. And the nice thing about the antiderivative of 1 over u is it's something we learn with our basic rules, right? It's kind of the trick case. You want to use the power rule here, but you can't use the power rule here because this is u to the negative 1 power. So this is the one where it's the natural log of the absolute value of u plus c. Don't forget that you shouldn't have u's in your answer because there were no u's in the question. So let's substitute back, get rid of this u, change it back into 3x plus 1, and I get 1/3 times the natural log of the absolute value of 3x minus 1 plus c. How about part D here? The antiderivative of x times 3x squared plus 1 to the 4th power dx. The u substitution that we'll need for this problem is we're going to let u be equal to 3x squared plus 1. If u is equal to 3x squared plus 1, then du over dx is 6x, so I could say that du is equal to 6x dx. This would be my third step according to the numbering that I did when I taught you this algorithm way up here. With these two substitutions, I'll be able to rewrite this question. If you look at this question, we can see the 3x squared plus 1 in here, so we can see where u will go, but you don't see a 6x dx. You do, however, see an x times dx. So what I'm going to do is multiply both sides of this equation by 1/6 and get 1/6 du is equal to x dx. With these substitutions, I can rewrite this integral. I got the antiderivative of, instead of 3x squared plus 1 to the 4th power, I'll just say u to the 4th power. And then instead of x dx, I'm going to say 1/6 du. I've changed all my x's into u's. I can take the antiderivative. I have this constant of 1/6 that I'll pull out in front of the integral. I got 1/6, the antiderivative of u to the 4th du. I can figure out the antiderivative of u to the 4th. I'd have to use my power rule. So I'd first change that exponent up to a 5, but then I'd make sure that I put a 1/5 down in front so that when I'm taking the derivative of u to the 5th, the 5 and the 1/5 would cancel out, and I'd get up to this u to the 4th. And then I'll tack on a plus c. At this point, I'm just about done, although technically I shouldn't leave u's in my answers. 1/6 times 1/5 is 1/30th. And then instead of u to the 5th, I'll write 3x squared plus 1 to the 5th power plus c. Before I get to this last problem, part E, I want to go back and look at A, B, C, and D again. And I want to take some time to talk about how I knew u was supposed to be equal to whatever I made u equal to. If you think about what we're going to do in this algorithm, the key points are we have to get rid of all the x's and change them into u's. So the way I choose what u is equal to is I kind of have to look ahead. I have to think about what can I make u equal to so that when I later figure out du, I'll be able to change all the x's and all the dx's into u's and du's. And that's kind of a tall task to do all at once. I can tell you from experience that what a lot of people do is kind of a guess and check method. They look at the problem, they focus on the variable. In this case, the variable x only appears once here. There's no x's down here or anything, it only appears up here in the exponent. I then try to make u take up x and as many other things as possible so that the du will appear up here in the integrand. So what I'm saying is the reason I knew to make u equal to 2x plus 1 is because then du would just be equal to 2x dx, and it'd be easy to get rid of this dx. It might have been tempting, for example, to make u equal to e to the 2x plus 1, right? That would simplify this thing even more. Then I could replace this entire e to the 2x plus 1 with just the letter u. But the problem with doing that is then I would figure out du over dx, and the derivative of e to the 2x plus 1 is 2e to the 2x plus 1. And now I'm not going to be able to change my dx's into du's because I'm going to have too many x's here. Right? I'm getting rid of all of these x's with this u. In order to change my dx into a du, I'd need another e to the 2x plus 1, which doesn't occur here. So the reason I knew not to use this is I'm looking ahead and thinking about if I use this, du is not going to work out very well when I substitute in. And I know that that's asking a lot for students to kind of see all that in the future. So really it's the kind of thing where you do a lot of them and you kind of get the feel of what u should be equal to. But it takes a little while to get comfortable with that. Some tricks that I can tell you is when you choose u to be a linear expression like 5 minus 3x, what that means is du is just going to be equal to a constant times dx. And constants are really easy to use with integrals because you can always just kind of pull them out in front and stuff. So you have a lot of freedom there. So when you're looking at a problem and you can do a substitution that gets rid of all of the variables with a linear substitution, that's probably a good way to start. 2x plus 1 is linear, 5 minus 3x is linear, 3x minus 1 is linear. In both A, B, and C, I was able to do a substitution that got rid of all of the x's and left me with something that I could take the antiderivative of by doing a linear substitution. And linear substitutions work out really nicely for the du part. Things get a little bit more complicated in part D where my substitution is not linear. Here I made my substitution 3x squared plus 1. The challenge with making u equal to 3x squared plus 1 is then my du is going to contain an x in here. Technically du is 6x dx, but I'm not too worried about the 6 because I can always move constants around really easy with integrals. It's the x that's problematic. Before choosing 3x squared plus 1 to be my substitution for u, I had to look ahead and make sure that there was another x that would get sucked up as part of the du. And that's the more advanced method of substitution. You really have to see all the different parts ahead of time. And that's asking a lot for students to do. What I can tell you is that generally what you're looking for is an expression like 3x squared plus 1 so that a multiple of the derivative of that expression. So the derivative of that expression is 6x, but I don't have to worry about the 6. So a multiple of this, meaning just the x times dx, shows up in the expression. I see the expression here and kind of part of the derivative of the expression right there. That's really what you're looking for when you're making your substitutions. Probably still feels really nebulous, so let's do one more example, and then I'll make a whole nother video doing more examples where we spend some more time deciding what u should be equal to. So look at this problem. What do you think u should be equal to? Well, there's only so many options, right? You kind of got an x squared, or you got an x squared plus 7, or you got an x, or maybe a 1 over x squared plus 7. you got to choose part of this expression and make it equal to u. I think what you're going to end up wanting u to be equal to is x squared plus 7. And the reason you'll want u to be equal to x squared plus 7 is because that's going to dramatically simplify this expression. It'll get rid of all this stuff in the denominator and just change it into one letter, the letter u. And furthermore, the derivative of x squared plus 7, which is 2x dx, also shows up in this integrand up to the constant. So you don't worry about the 2 here, you just focus on the x dx, and you see the x dx here, and you're like, oh, that's going to fit perfectly. Here's my u, and here's my du. You'll get to the point where you see a problem like this, and you kind of pick apart the little pieces before you write anything down right here. I know that's asking a lot, but trust me, through repetition, you will get there. At this point, second video, still kind of learning this stuff, trust me that u is going to be x squared plus 7. If you know that u is x squared plus 7, can you finish it on your own? What you'd want to do is figure out that du is 2x dx, and therefore half of du is equal to x dx, and now I can substitute. This question becomes the integral of 1 over u, because the x squared plus 7 is down in the denominator here, times 1/2 du, because I replaced the x dx with the 1/2 du. I got a constant, this 1/2, that I can pull out in front of the integral symbol. So all I got to do is figure out the antiderivative of 1 over u du. Remember, this is kind of the tricky one where you're thinking you should use the power rule, but you don't want to use the power rule because this is u to the -1 power and it would cause you to divide by 0. This is the weird one where you use the natural log of the absolute value of u for the antiderivative. And then you take it one step further. You don't want to leave u's in your answer. So my final answer would be 1/2 times the natural log of x squared plus 7 plus c. On this problem, as well as all of the above, you can check your answers by taking derivatives, and when you do so, you should see some chain rule going on. But when you get really good at these, you won't even need to check your answers because you'll be so confident in the algorithm in its own right. I think I want to stop this video here, but I hope you don't think that I think that you should be an expert on the substitution method at this point. It's a really hard method. It takes a long time for people to wrap their heads around. I'm going to do a whole nother video with even more examples. And then on the homework, you'll get lots of practice, and by the end, you'll be an expert with U-Substitution.